thanks again, Ian. It was an absolute pleasure. Quite a change of scene to come from sleepy Melbourne over to the Paterson lab and do a PhD. I'm sure it's changed my trajectory in incredible ways. So I'm going to tell you a little bit of a story about sulfate metabolites now. So let's dive right in. So we do a lot of our work on anti-doping chemistry. We work with testing labs and so on. And of course, drug metabolism is really important. It's important in anti-doping chemistry. It's important in therapeutic development. So something like a steroid, like testosterone, gets metabolized. Phase 1 metabolism is oxidation and reduction, hydrolysis reactions, hydroxylations, things like that. And then we have phase 2 chemistry, which is conjugation with glucuronic acid or sulfate. And these facilitate excretion from the body. So last time I talked a little bit about glucuronides. I'm going to talk about sulfates in this talk. And the first little project I'm going to talk about is indirect detection. And this is identifying enzymes that can hydrolyse these sulfate esters. And why is this important? Well, so here's two examples from the anti-doping world. Methyl testosterone is a synthetic steroid, quite easy to detect. But one of the sulfate metabolites that you form is that molecule in the centre top there. So when this was discovered, it extended the detection time for methyl testosterone by 2 to 3 times. So that's quite important. The molecule below obviously is testosterone. It's endogenous hormone. A lot of athletes like to use this because it's hard to detect. And again, there's a way to do that. I'll talk a little bit more about this later on. By looking at one of the metabolites, epiandrosterone sulfate. So sulfates are important. But key to studying them might be the need to hydrolyse these sulfates. You can do this with strong acid, but it's pretty rough. Or we can maybe use an enzyme, which is very mild. So looking around at how we might do this, we came across this paper from 1977, and this was a study of a whole organism, Pseudomonas aeruginosa. They isolated this from a fecal sample, and they were growing it in a sulfur-starved environment. And of course, bugs don't grow where there's no sulfur, so they need sulfur. And then they threw in lithocolic acid sulfate, which is the molecule on the left. And what they saw was that the bug now grew. And of course, it grew because it was harvesting the sulfur from the sulfate ester. They also detected the lithocolic acid as the product. And so this suggested, it's a whole organism study, but it suggested that this bug had a sulfatase enzyme. So of course, we went away to the genome of this organism. We found the gene which encoded the sulfatase. We bought that gene, we expressed the enzyme, and purified it, and away we go. And so here's a little bit of a study of how that enzyme works. It's a very complicated table. Across the top is a range of different substrates, and you can see them on the box on the right. Don't worry too much about that. On the left-hand side, in red is our enzyme. I'm going to call that PAS from now on, Pseudomonas aeruginosa sulfatase. And then all of the other commercially available sulfatases you can buy from Aldrich. And basically, the bigger the number or the darker the box, the better the activity. And what we see is that our enzyme is about as good as the best commercial enzyme, Helix pomatia sulfatase. The big benefit is that we've got a purified enzyme with a single enzyme activity, whereas all of these others are crude enzyme preparations. So Helix pomatia is just squeezed out of a snail. And so there's lots of other things potentially going on, and we know that now as well. Okay, so we're about as good as the best commercial enzyme. Can we do better? And yes, we can. So the crystal structure of the Pseudomonas aeruginosa sulfatase is known. And so we decided to take a process of directed evolution where we would modify the amino acid residues around the binding site, 1 or 2 at a time. And you can do this with techniques like site saturation mutagenesis that screen through all the possible amino acids. So you get a large number of combinations, of course, and so we plate out all these different enzymes in 96-well plates, and we screen through with LCMS for the reaction at the top there, hydrolyzing testosterone sulfate. We get some hits there, we confirm them, we can eventually purify these enzymes and do kinetics and so on, and at the end of that process, you get a better enzyme, right? So that's great. Well, we don't have to stop there. We can take that new sequence, we can chuck it in at the start and go round and round and round. And so we did that for a few times, and here's the summary of the results. And so the box on the right-hand side just shows that after a few rounds of evolution, we've got enzymes that are 150 times better at hydrolyzing testosterone sulfate than where we started. And the box on the left-hand side, this PVFV PAS mutant, is really good because it's got a much broader substrate scope than our original enzyme. And so both of these features are useful. So arguably we're better than the best commercially available enzyme now, not just because it's purer and a single activity, because it's just better, right? So here's that example of testosterone doping. So take testosterone, hard to detect, but one of the best ways to do this is to look at this epiandrosterone sulfate molecule. And our collaborators in Cologne used our enzyme to hydrolyze this back to the free steroid, and then you can do GC, carbon isotope ratio, mass spectrometry. And I won't try and explain those diagrams on the right because it would take me 20 minutes. The other application we've had for these enzymes is in vitamin D. So, of course, vitamin D comes from this 7-dehydrocholesterol here. And there's a couple of steps before you get to this intermediate here, which is 25-hydroxy vitamin D3. And this is one of the markers that they use to assess your vitamin D status. Okay? So just look at the graphs on the left there. A is just looking at vitamin D without any hydrolysis of conjugates. And there's three groups because there's people with no vitamin D supplementation and there's two groups with different supplementation regimes. But you get a certain level of this precursor. The middle plot then is when you include hydrolysis enzymes, and you can see that the levels are higher. And the last plot, C there, just tells you that roughly half of the vitamin D is conjugated when it's circulating in your system. So if you want to know someone's vitamin D status, then you need to look at the conjugates and you need to hydrolyse these different conjugates. And so this is how you do it. So you're looking for the precursor on the left using your analysis. You can buy the E. coli glucuronidase enzyme from Roche and that'll cleave the glucuronide. That adds another 4%. And then, of course, the sulfate there on the right-hand side is about 45% of the vitamin D precursor there, and you use our enzyme to get to the free form. So another interesting application, I think. So just to conclude this little story, we've found a new enzyme that can cleave sulfate esters, and now it's better. Let's talk about direct detection. So now instead of hydrolyzing sulfates, why don't we just detect them directly by LCMS, for example? So that's the story I'm going to tell you now. And this was a sabbatical that I did in Barcelona. It was a great time. And when I arrived, this was the question, right? So here's this methyl testosterone and it metabolizes to this sulfate, but the eagle-eyed amongst you might have noticed that the D ring, that's the one on the right-hand side, there's been an epimerization. Fair enough. Here's the proposal. So you get the phase 1 chemistry, you get double sulfation, and then the tertiary sulfate's unstable, so it hydrolyzes with inversion of stereochemistry. And that all looks entirely reasonable, but it wasn't clear to us whether these bisulfated, these doubly sulfated species actually existed. So we decided to go and have a look and see if we can find them. So here's my one synthesis slide, Ian. This is a sulfation of a steroid diol here. It's a chemistry that was developed in the 60s and it still works. I guess the only innovation we made was to use sort of analytical weak anion exchange solid phase extraction to purify these. And so you can purify these reactions in a matter of minutes. So we've done lots and lots of these examples. And once you have a library of these, you can start to look at how they behave in mass spectrometry. And so they all, the left-hand mass spectrum there, they all tend to ionise as the dianion. They're really strong acids, so that's not surprising. And then when you subject these to fragmentation, they all tend to lose hydrogen sulfate and leaving behind this steroid monosulfate ion. And if you look at that, what you see is that the mass to charge ratio does an unusual thing for a fragmentation. It actually goes up because we've lost a charge. So you can develop a little bit of a mathematical formula that explains this phenomenon. It's fairly simple, I guess. Or you can just develop a list of precursor to product ions that you would observe for these bisulfate species. And if you extend that list long enough, you can cover the whole steroidal range, and that's what we did. And so we call this process constant ion loss, and so we call this a kill scan, looking for these bisulfate products. And the first one was an easy one. This was known that tribolone, another steroid with some anabolic activity, gives this bisulfate. And so we took samples pre and post doping. So again, we're looking for this constant iron loss process. On the left is the urine sample pre-drug administration, and on the right is the urine sample post-drug administration. You see that nice big chromatographic peak there, which is a signal of that metabolite. We've also applied this to the prenatal diagnosis of problems with steroid biogenesis. And so reasonably early in the pregnancy, I guess the unborn baby starts to synthesize their own steroids, starting from cholesterol, you're cleaving back the side chain until you get to something like DHEA, which is the sort of precursor for testosterone and estradiol and things like that. It's also eliminated, so it gets hydroxylated at the 16 position, and then passing through the placenta, it turns into estriol, and you detect this in the maternal urine as estriol glucuronide. So it's not just your own hormones sending you mad, it's also that of your unborn baby. So there are sometimes problems with steroid biogenesis. So a condition called P450 oxido reductase deficiency slows down or blocks some of these steps. And so you end up with a sort of a blockage and a build-up, and these start to come out. So you get a pregnane diol in the placenta there, and then a pregnane diol bisulfate coming out in the maternal urine, and you can detect this. And so here's an example at the top. Is the chromatogram for a normal pregnancy, where we see the estriol glucuronide, nice big peak, a little bit of the pregnane diol bisulfate, and on the right-hand side we have no estriol glucuronide and a large pregnane diol bisulfate peak. This is indicative of problems with steroid biogenesis. And we studied 4 related conditions in this kind of manner, and the bisulfates turn out to work in all of them for detecting these problems. So in conclusion, synthesis of sulfated things is pretty easy, but because you can do that, you can develop new mass spectrometry tools and advance things like diagnostic applications. So the last thing I'm going to talk about is looking at sulfates more holistically. And so we want to detect all sulfates now, everything that is produced, say, in a urine sample. And so we've developed this pipeline. It's metabolomics. We do LC mass spec, tandem mass spec. We have a process where we take the mass spectrum, plus tandem mass spectra data, so fragmentation data. We can then do some coding and so on to categorise things into sulfates and non-sulfates. We can do some statistics, and out the end comes a list of all the sulfates that you see in your sample. So how do we do that? We just use a fairly routine sort of instrument. I guess most departments would have an instrument like this. It's a high-res mass spec, but it's got a quadrupole on the front, so you can select ions and fragment them. And as we're running our sample, chromatographically, we're acquiring data in this manner. So we'll do a survey scan. This will detect anything that ionizes in that particular window. And then we'll do a data-dependent acquisition and fragmentation. So for the top 5 precursors, we'll pick up, pick those, we'll select them in the quadrupole, we'll fragment them, and so we have MSMS data or fragmentation data. And so that process repeats. There's a few things in there, exclusion lists, which just limit the repeat sampling of intense ions or remove ions that come from the method, the solvents, things like that. But it's a fairly straightforward process. And the good thing about sulfates is that their fragmentation is really, really predictable. And so you get one of these 4 ions, or you get these 2 neutral losses across the top there. So all sulfates that we've looked at do one of these, or sometimes several of these different processes. And so have a look at testosterone sulfate at the bottom, you fragment that, and you get this nice 97 mass to charge ratio, which is hydrogen sulfate, okay, as essentially the only ion. So this means we can use this information to pick sulfates from non-sulfates. And so we use all of these different transitions, plus we calculate 2 other characteristics: maximum abundance, which is just the maximum sulfate reporter ion, and the intensity ratio is just the ratio of the sulfate features to the non-sulfated features. And that just allows us to develop a pretty picture there, where the orange things are the sulfates and they cluster in the top right, and the black things are the non-sulfates, and they cluster in the bottom left. And we've used an algorithm called k-means to basically separate the data. And you can see the violin plots on the right just sort of give you an indication for how well those two groupings are separated. Sulfates do behave very predictably. So here's our analysis. We're doing testosterone doping in a horse now, testosterone propionate. We have a sample after doping and a sample before doping. We're going to compare. We have a few controls and QCs and things like that. When we do our analysis, we get something like 6,200 features, of which about 3,500 have NSMS data associated with them. So we can say something about their status. Are they sulfates or non-sulfates? And of those, once we do our k-means clustering, we get 962 sulfated features. What's more, we do things in triplicate, so we can do a bit of stats. So here's a volcano plot. It's got fold change on the bottom and a significance on the y-axis. And we're interested in this region in the circle, which are upregulated sulfate metabolites. So the plot on the right is the sulfated features. Look for the things in the circle. And when you do that, we can putatively identify 10 sulfated steroids that might potentially arise from testosterone propionate. And of these, we've managed to identify 4 of these at this stage by synthesis and comparison. And so that's a pretty good outcome. But we've got a little way to go because we don't know whether these are really that relevant. We have to do longitudinal studies and population studies to work that out. Whoop. So just to conclude, we've developed a nice method, I guess, to analyse the sulfate metabolome. It's more comprehensive, and we've applied it to doping. We've also looked at our enzymes and just shown, without doubt, that they are better than the commercial enzymes because they don't mess up every other type of metabolite. They're selective for sulfates. So I'll just conclude by thanking the students and postdocs who did the work on the left-hand side there, the collaborators who we've worked with on the right-hand side, and of course the people who fund us on the bottom. And thank you for your attention.
Okay, so